Well, we continue with what we did last time. So, recall last time we already defined what is the group cohomology. The right derived functor of the left exact functor of the fixing point of G on the G module. And we are left with one exercise last time, so we deal with this exercise as we continue with the next section. So this exercise said a G be a finite cyclic group with discrete topology, so there is no problem with continuous. Order n axon having group A, prove the following statement. The first one says an element from the cycle, from the cocycle, is determined by the element acting on S, where S is generator. Okay, so G is a finite cyclic group generated by S. Show that this is determined by Fs. Okay, so of course people fail in that. Okay, looks like F should be a group homomorphism, so any element can be presented as power of S, so it should be like this. But actually no. The problem is that F is not necessary to be group homomorphism. As we saw, what F should do is FGH should equal to GFH plus FG, if I'm correct. Let's see if I'm correct. It's our description. Yes, with our description. FGH should be GFH plus FG, phi GH. Yes. So you see, F is any function from group G to the abelian group A. Okay, any function application such that we have this. So FGH is not FG plus FH, which means that somebody may wondering if here we consider the cyclic group with multiplication, here the abelian group with summation. People would ask if this is true, right? I say this is not true. This is only true when what? When G acts trivially on A, this is just FH plus FG. Okay, so what do we do? Proof. Since we have this, so in particular Fs squared. Okay, it's not Fs plus Fs, but it's Fs as acting on Fs plus Fs. This is good enough for us, which tell us that fs squared equals fs, 1 plus s acting on fs. Okay. As group homomorphism. Recall that when we say G module, we mean this is a group homomorphism from G to the automorphism ring of A, which means that if G1 gives automorphism and G2 gives automorphism, then phi G1 plus G2 should equals phi G1 plus phi G2. Okay, what does this tell us? This tells us that when we write 1 plus s dot f, what we mean is actually phi 1 plus s evaluate on the element of A. It equals phi 1 plus phi s. So actually this condition, this is group homomorphism, tells us that okay, that's why we write like this. Well, this is something very stupid, right? But I'm just telling that it's not easy. It's not euro to just say A is a G module, but G is not ring. Usually when you see it's G module or it's a ring, a module ring R, you mean, you know what you mean? You mean the multiplication in R and the summation in R are preserved when it's acting on the element of this module. But here is just a group. What do you mean by group homo? What do you mean by G module? As we said, except those conditions on the continuity of the homomorphism required, this is continuous. Besides that, we say actually there is a group homomorphism from G to automorphic ring of A, which just means that okay, it's not a ring, but you have to satisfy all the rules as a module. Just ignore the one requiring on the multiplication with G acting on A is the acting on A is the multiplication. Is the acting on A associativity. Okay, so this is something very stupid, right? Just forget it. Okay, forget all those things. Okay, it's two conditions. Our requirement, our definition of G module. Okay. So we have this. And continue with this. What do you have? And do the same thing for S cube. What is it? It's S acting on Fs plus Fs. What is it? It's S acting on just, sorry, this square, of course. Just putting this square inside. Fs plus Fs. Okay, sorry, it's stupid like this. You can even more clearly as what we write here, just 1 minus S multiply Fs plus Fs. It is what is 1 plus s squared fs. By induction, it's obvious. We got what? Right, from 0 L minus 1 acting on fs for L bigger or equal than 2, right? Because fs is okay, it's also okay. Problem less equal than minus 1. So this finished the proof of the first one. What's the next? What's the second? The second says that the element fs satisfies the condition. Okay, which we already proved. Almost, not already. So we have to prove this is what we have to prove. But as you saw, what is this? Proof by 1. This is just f s to the power n, which is f0, which is 0. But be careful. Why do you have f0 equals 0? Are you sure? Since, as we said, it's just a function satisfies certain rule. You're feeling it should be 0, maybe it's not. So you have to check it. How to check it? For example, since we know, as what we already said, we have this condition. Can this condition lead us to the conclusion here? For example, f0. Well, it's not very friendly to write 0. I think I should write 1 if it's nice. As for me, my notation is to multiplicative on G, summation on A as a group. So let's say, so f1 should be 1 times f1 plus f1. What is 1 acting on f1? This is, as I said, what they regarded as special kind of module. So this tells you this trivial action should still be f1, or you say that there is a group homomorphism from G to automorphism of R, so the identity of G must map to the identity automorphism. So acting on f1 should be f1, so this is 2f1. Which implies f1 is 0, okay? So we finish this one. For the third, well, we have to say this is a very easy case, since we are firstly dealing with discrete topology. Secondly, it's finite and cyclic. You see, they're both very restricting conditions, so it's a very easy case. You just have a favor of what is going on, what is happening. Okay. The third one says the set x minus s acting on s, x is containing something like the trace. Okay, that is in fact a subgroup. So those elements, a subset of the elements is a subgroup. That's what we have to prove. So what do we have to check? First we have to check its subset. So summation G acting on S minus S x. What is this? This is just G acting on X minus itself. Okay. Which is the same thing with. So is it a subgroup? How do you check its subgroup? So if X, Y, so this X in A, right? So this is already a subgroup of A, submodule of A is a subgroup. So the law is addition. So we want to claim that X plus Y minus X plus Y is 0. So this is yes, because again though this is automorphism, real automorphism, so this is just Sx plus Sy then combined. That's obviously 0. Okay, I think there is nothing to prove for this statement. What is the force? The group H1G is isomorphic to this, in particular if the action is trivial. It's just the group homomorphism from G to A. Exactly. So hence G is a finite order n. This is just torsion for A because it's cyclic. Okay, because it's cyclic. Okay, so let's prove this. I would like to remove this a little down to make it easier. Okay, let's just continue. Okay, so we want to prove H1GA equals, what should be here is what we know. Here we have crossed homomorphism, call it crossed homomorphism, quotient by principle. Principle crossed homomorphism. What should they be if you do not? Check it. So it should be those phi satisfies for any element L, N, L. This is what it should look like, right? Principle is there exists some A, right? This is what it should look like. Well, but now what do we prove? We prove that okay, so this part is obvious. Okay. Okay, you see, we prove this is a subgroup of this. So we have to prove it is isomorphic too. Is it just describing the yeah, it's describing the element of A, you see? It's X minus S times. So I'm suspecting here I write the opposite. Okay, so how do you build a morphism? Yes, the problem how you define morphism from this group to this group. Actually, how do we do it? Actually, this morphism is obvious. So we build a morphism. Which is our notations. By sending phi to what? Phi s. And we already proved phi s actually is in the trace theorem. This is what we proved. And déjà yes. Wow, this is nice. This is nice. You see, you have this with our description here. You only have to prove only have to prove the size containing the kernel. And prove this is surjective. So once we can prove this is surjective, this one is surjective, and you prove the kernel of this is this one. Okay, so the first step, you prove this is surjective. The second step is you prove this is the kernel. So why this is surjective? To prove this is surjective, you have to prove any element with this, satisfy this, must. So if phi s equals 0, then we claim can we prove this? Well, these two actions of any element here is obvious. Satisfies this. Conversely, how do you conclude? How do you conclude conversely? It's a little messy claim like this. Let's just be easy. If I define sending S to A, okay, the S squared to S multiplication of A plus A. What is S on A? It's already there. Once you got A, you got the action. The G module already got it. And so on. Okay. The 1 to 0. Because we defined on each element correctly. I mean, this is just function. Tell me the image on each element. So I already define a function. You have to check by this definition. One checks phi SL. SL equals SL phi SL plus phi SL. just check it. You will say, okay, it works. Okay, now we see what is the kernel. The kernel of this homomorphism. An element whose trace is 0 that is also killed by S. Since we are sending phi to phi S, so if X satisfies this is telling us that phi S if this is the case, no, writing something wrong. It is if phi S equals then let's see, claim for any element there exists some element making this. Let's just check it. So if I say this, then phi square is S. Sorry, here's not A. This is phi A precisely. Phi S. Phi S is, well, this is misleading. I do not use A here, okay? Alpha. So what is this? Okay, see, fast. There is this alpha. Then fast square is still in this form. There's some alpha. It's alpha in A, so by induction you can do the same. You will see. It means that all the kernel of this map comes from here, and you are left to say that all the elements here map into 0, map into 0. Okay, so what does this mean? If phi s an element equals some a any L, yes, this alpha must be the same. It's not strange to be the same. It's our definition. We have to be the same alpha for any element here. Okay, it's the same alpha. So here, if it is exists some a for any L, then in particular, okay, so this means that we're mapping to here phi s, the phi s you map into this quotient ideal. This is 0, the quotient ideal, which implies that the kernel of this step, of which step of this both, okay, kernel this composition is just okay. Then the next one is group annihilated by n, scaled by n. Yes, because this is just so any element here f f is function from G to A. So this is a group, it's T module, okay, that's something group. But what is NF? To mapping any element to G. To what? What is NF? F is the function from G to A. NF, actually it is the function from G to A, sending one element to the same image that multiply itself n times. So this n is actually acting on A as the happening group, which means that so it's 0. This said if A is of order n, then it's also killed by M. It's the same story, just M okay, sorry. So for this one, it's the story we just told, because A is of order M, so acting M times, for sure it's killed, but why is N killing? Well, suddenly I'm feeling that I did something very stupid. So I'm coming back to my first answer. It's not something very serious, but it's bad notation. Actually, we didn't use nice notation because G is considered as a multiplicative group. How can you do summation inside this group? So this is, we understand well what it is. This is just summation inside the subheading group A. So we don't use the bracket, we write what it is. Okay, a square is just, if you formally you can write like this, but it is itself. It's S times Fs plus Fs. Well, you can write like that. What you mean is this, it's not inside G, this is inside automorphic of A, okay? This is a building group. This is a group, as I explained actually. But what is funny is so actually you're sending you must, okay, you must sending phi 1 to the identity morphism action. It's really like the module. Why am I missing myself? Okay, so as a notation this is okay, but this is not, you cannot say this is coming from which element acting on Fs. I was stupidly thinking, okay, I stupid mistaking this with 0 process, so it's okay. It's just notation. It's just notation, okay? As element of automorphism, you know what it is. Okay, let's see if we claim any f and the F so then B minus this is what we want. We want to prove if F is inside the 1GA and Fs equals A, then there exists B such that F equals B minus SB. And this tells you once this holds, then it holds for any S square. If you have this, then okay. This is commutable, okay. Closest supreme homomorphism from S to the automorphism. Yes. This is not nice, right? Yeah, if we find the element such that this holds, then we're using this condition to say if it's satisfied. We want to use induction to say this holds for any element. Then you use induction. Power of S squared, then it's N times Fs squared. fs summation inside A, but fs square must satisfy s times fs plus fs, no problem. And n acting on s acting f is like it's like the summation n times on this element. Equal s to the power n fs, right? It also says it is also fs itself. Also, what you write is right here. We just ignore this. Simply, we just made a stupid mistake. Here, you see, it's B. Okay, of course it's B. We made a stupid mistake. So it's just this. So you see, really, it's the same B. Okay. So really, once you can prove this, then you prove NS using induction. On N, we got the same result. So we only have to prove this. There is this B. So we solve it. We just solve this. We claim B just equals how to solve this. Just notice N A equals S you see, because S to the power N is identity of the multiplicative group, so it's acting on B trivially. Okay, you see, okay, this is no problem, I agree. Then what? Then what? Then you have to notice that this is also S times S to the power N minus 1 acting on B minus S. This is G mod. Okay, it's a G mod. So you first multiplication inside G, then you send it into automorphism. It's the same as you send it into automorphism, then you summation inside A. Okay, tell the B is just S. You just define like this. Then you say let's just be careful, just repeat what we did. Don't be so hairy. If we have this, then b minus sb, s to the power nb minus sb, do the same thing. It's sm minus 1 times b. Okay. Now we finish this very stupid, very most difficult one, I think. How can you just the amazing, strange thing is this. Well, it's not strange, it's just like the module structure. Okay. Anyway, so the last one is in this case, if m and n are co-prime, then this is 0. This is obvious, since it's killed both by m and n. If co-prime, they're killed by 1. Identity. And the last one is this is 0. For any action between group A, because in this case G is Z, so the G is just itself, right? So you just consider this functor. I mean, you just compute. You can use this factor to compute, but this is 0. This is exact. This is projective Z module. The exact factor. Apply this is vanishing. Okay. Wow, in this case it's not only 1. Okay. Any I should vanish.